guys, good morning. I hope you're all doing well this morning. Welcome to your first online math lesson. We are going to be covering lesson 25 today, which as I was reviewing it, I'm pretty sure we did it already before the break. But I'm going to go over it again because it was a lot crammed into the first day, and I think some of you may still be working on some of the practice pages, and so I wanted to just kind of take this time to go over it a little bit more in depth. Just a note, if we do finish early, I'm just going to go ahead and head on over to Google Hangouts for that remaining time, and so I will be available there for questions. I'll always be available for questions between 10 and 11 on Google Hangouts, but if we finish up the math early, I will just go ahead and head on over there as well. So let's go ahead and get started. So the lesson that you guys, so again, I think that this is a lesson that we've already covered, but I just want to go over a few extra points with it. So hopefully most or all of you have your lesson books and your practice books at this point. I think everyone has either had theirs delivered or has been able to pick theirs up on Monday. So we're going to go ahead and just step through the lesson in your book, and then I'll assign you guys practice pages. Like I said, since it's a lesson that I'm pretty sure we already covered before the break, you may already have your pages in practice, but your practice pages, you may be working on them already, but I wanted to just go ahead and get started with that. So we're going to be on page 260 in your instruction books. So please go ahead and start off by turning to page 260. You'll notice that lesson 5 is talking about length, liquid volume, and mass. So we are in our measurement part of our math focus, our measurement strand. And this particular lesson, like I said, is really trying to take a whole lot of information. So it's starting off with length, so measuring things like you would with a ruler, so that you can measure how long something is or how tall something is. If you are measuring liquid volume, you would be measuring the amount of liquid that fills a space. So volume has to do with filling a space. And when we talk about liquid volume, if we talk about just volume, we could take like maybe a cube and think about how many units, how many square units we could use to fill it up. When we're talking about liquid volume, if I were to dump out my water bottle, all the water would spread out. So we're talking about how much liquid would fill something. And you may have noticed on your, well, I think mine's on the bottom on this one, but you may have noticed on some of your water bottles that it has little increments. Some of them have milliliters, some of them have also, sorry, something beeped at me and I don't know where it is. Anyway, so some of them have milliliters, some of them have ounces, some of them have both. So those are just some of the ways that we, some of the units that we use to measure liquid volume. But basically the concept is the same. It's how much area would be inside a space that you could fill with liquid. The last topic is mass. And mass really refers to weight. I think technically with the science aspect of it, it refers to like the density of how much something weighs. So when we're talking, so weight and mass sometimes are used kind of interchangeably, but technically mass has to do with how dense something is, and that relates to the weight. So let's jump in. So if you have already turned your book to page 260, you'll see that the first question is that Julia's family is visiting an amusement park. A sign says a person must be at least 45 inches tall in order to board the ride. Julia knows her younger sister was 3.5 feet tall at her last doctor's appointment and has grown 4 inches since then. Is Julia's sister tall enough to board the ride? Now, the crucial part of this particular question is noticing the units that it's asking. So units, remember, refers to the way we measure something. So earlier I referred to the liquid volume measurements of ounces and milliliters. There are we have different standards of unit. We have different standards of measurement, and it just depends on what we're measuring and also what the best application is. So sometimes, like in this problem, we have inches as well as feet. So I think we talked last time we met at group about how inches are smaller, feet are bigger. And so depending on what you're measuring, if you're measuring something that's small, like my pen, then inches would probably be a better unit that would fit, because if you used feet, it would be too high, and so you would have to be using fractions of feet. And so we just go down to the next unit of measurement, which in this case would be inches. Same thing if you're measuring really long distances. If you were measuring, for example, the length of a trail, it would take a really long time to measure it out in inches. And that wouldn't be the most useful application. So using miles or even feet, depending on how long the trail is, would be a much better fit. You can think of it too, like our last read aloud book, The Phantom Tollbooth, when they get to the Mathematicians Digitopolis. There is the sign that has all the different ways that you can get to Digitopolis and how long it is, and but really they were all the same length. It was just that the units changed. So so it's important, especially in this beginning problem, to make sure that you are using your awareness of what the units are, so that you can then go ahead and check that out. So so I'm just going to go ahead and go through the problem again, just focusing on the key pieces of information. So science says that a person must be 45 inches tall in order to board the ride. So the units that we're talking about first are inches. And the information that we know is that the ride requires that somebody be a minimum of 45 inches tall. So they can be taller than 45 inches, but they can't be shorter than 45 inches. The other piece of information that we know is that Julia's younger sister was 3.5 feet at her last doctor's visit, but she's grown 4 inches since then. So she's 3.5 feet plus 4 inches. Now, we have two different units of measurement here. We have feet and we have inches. And so it's really, so we can't compare these right now because we don't know how many inches would be in feet and inches. So we have to do what's called a conversion first to be able to compare them similarly. So when I said we don't know how many feet and inches and feet, we do actually know how many inches are in a foot, but we can't tell from this problem. So we're going to have to go ahead and take our 3.5 feet and we're going to convert it into inches, because our problem is dealing mostly in inches. It's saying that the minimum height for the ride is 45 inches. So we don't want to convert it into feet. We want to convert it into inches because we want to see what her height is in relation to the minimum amount for the ride. We also, we have feet, but we're also adding inches to it. So that would be another indicator that we're going to be moving into inches. So if you don't know this already, there are 12 inches in 1 foot. So if I were to write that as a math equation, I would write it as 12, and IN is the abbreviation for inches, is equal to 1, and FT is the abbreviation for feet or foot. So 12 inches is equal to 1 foot. So that means that for every 1 foot, I have 12 inches. So now Julia's sister is 3.5 feet. So if I think about 12 for each 1 foot, I have 12 3 times because she's 3 feet tall. So I'm going to start with that, and I'm just going to say 3 times 12. And we're going to figure out how many inches would be in the 3 feet. So when I multiply by 12, I know that it can seem a little intimidating because you're dealing with double digits, but really the distributive property of multiplication tells us that we can break up this number however we want. And I'm going to show you that it's actually really easy. So 12, we know we could break out into 10 and 2. So 10 plus 2 is the same thing as 12. And so I really like multiplying by both of those numbers. I like multiplying by tens because I can count by tens super fast. And I also like multiplying by twos because you can count by twos super fast. So 12 is actually pretty easy because when you're multiplying any number by 12, you can just think of it as multiplying by one set of 10 and 2 ones. Or you can think of it as multiplying by 10 and 2. So in this case, I'm going to think of it in terms of 10 and 2. 3 times 10 I know is 30. Then I'm going to go ahead and take the other part, 3 times 2, because remember, this whole thing would represent the 12. So I want to multiply the 3 by both parts of it. 3 times 10 is 30. 3 times 2 is 6. So I would have 30 plus 6, which we know is 36. So we now know that 3 feet is equal to 36 inches. But that's not the full height of Julia's sister. She's 3.5 feet. So I'm going to go ahead and erase this bottom part, and let's think again about what we know about our conversion, which is that 12 inches equals 1 foot. So if we know that 12 inches equals 1 foot, how many inches do we think would equal half a foot? Well, half of 1 is 1/2. And so to keep our kind of balance equal on both sides, so you can think about your equal sign as kind of like a balance. What you do to one side, you have to do to the other in order to keep it equal. If 1 is now halved, then I'm going to take 12 and I'm going to half that as well. So if I think about what is 12, what is half of 12, I could think of it 2 different ways. I could think of it as 12 divided by 2, which would be half of 12. Or I could think of it as what plus what equals 12. What 2 times would equal 12? Well, I know from my doubles facts that 6 plus 6 equals 12. So I'm going to say that half of 12 is 6. And if we were to do it with the division way, we would see that 12 divided by 2 indeed would be 6. 6 times 2 equals 12. So 6 inches is equal to half a foot. So now we already had 36 inches from our 3 feet. So I'm going to go ahead and add, move this over actually, 36 inches from the 3 feet. I'm going to add the 6 inches here from that half a foot. But then she also grew 4 inches. Oh wait, so we have our conversion here. We have 3.5 feet that we've now converted into inches. We have 36 inches plus 6 more inches. I'm going to go ahead and do the ones first. I know that 6 and 6 makes 12. So I'm going to put the 2 in the ones place, have that extra group of tens up with my 3 tens over here. 3 and 1 more would make it 4. So I have 42 inches is the same as 3.5 feet. So I'm going to go ahead and write that up here in my top corner, 42 inches so far. But we also read in our problem that 42 inches was Julia's sister's height at the last check-in, but she's grown 4 inches since then. So I'm going to add 4 more inches onto her height. So I have 42 and 4 more. I'm going to once again go ahead and look at those 1 places. 2 and 4 I know make 6. So together I would have 46 inches as the height of Julia's sister. So that's her total height. So we've done all of the steps so far to find, first of all, our comparison with the height minimum for the ride. And we've also added on the additional 4 inches that she's grown since her last check-in. So now we need to go ahead and compare with the minimum requirement for the ride. So the ride says that you have to be 45 inches minimum to ride. And we just found that Julia's sister is 46 inches tall. Now, we could approach this in a couple of different ways. The easiest way is just going to be to look at these and say, is 46 more than 45? Well, yes, it is, because we all know that from counting, 46 comes after 45. It is the next one over. So Julia's sister is 1 inch taller than the ride minimum. So she can ride on the ride. However, we can also, if it were a little bit more difficult to tell, this one's an easy one to tell because we can do it just from sequencing, the counting. If it were a little bit more difficult to tell, we would maybe want to do a comparison to find the difference. And when you hear the word difference, you think, if you said subtraction, you got it right. So we could find the difference as well. So I would start with my larger number, 46 inches. Take away 45 inches, we're left with 1 and 0. I'm not even going to write the 0 because it's coming in the first place before the 1. And so any zeros over here aren't going to make any difference. So I have a difference of 1 here. So again, Julia's sister is 1 inch taller than the ride requires. All right. So if we are going to look through the questions of the problem, A says, describe how Julia can figure out if her sister is tall enough to board the ride. So what was our first step? First, we took Julia's sister's height in feet and we converted it into inches. And then we added her, we added all of the inches that would make up Julia's sister's height and compared them to the height minimum for the ride. So so first step, converting Julia's sister's height to inches, and then comparing the total number of inches to the 45 inches for the ride. B says, what unit does Julia need to find out if her sister is tall enough to board the ride? Inches. How many inches are in each of these lengths? So 1 foot we know equals 12 inches. 3 feet, as we found out, is 3 times 12, which would be 36 inches. And half a foot would be half of 12, which we found was 6 inches. So you can go ahead and fill in those numbers for C based on what we have already discussed. D says, how many inches are in 3.5 feet? So once again, we've already found out that 3 feet equals 6 inches, a half a foot equals, 3 feet equals 36 inches, a half a foot equals 6 inches. And so we would add those two, 36 plus 6. We got as our answer 42 inches as the total number of inches of 3.5 feet. E says, how many inches tall is Julia's sister now? So we had the 42 inches from the 3.5 feet at her last check-in, plus the additional 4 inches that she's grown since then, to give us a total of 46 inches tall. The follow-up part of that question says, is she tall enough to board the ride? The minimum requirement is 45 inches. So yes, Julia's sister can board the ride. Hooray! On the next page, on page 261, they have a little comparison here, so that they're breaking it up into, they're modeling it as units. So showing that there are 12 units, each unit representing 1 inch. 12 of those representing 1 feet. We have 1, 2, 3 feet. And then we have an additional half foot next to it. And then we're adding on, so we see that we have 36 inches plus 6 more inches for her height at her last doctor's check-in, knowing that you also need to add on 4 additional inches. So just another way to think about the problem. On the bottom of page 261, where it says reflect, it says number 1, explain why it is important to look at the units for the measurements in a problem before you start to solve the problem. So this is the most important part of this lesson. Why is it important to look at the units? Well, if we had just gone based on the numbers, we had 3.5 and we had 4. So if we had ignored the units and just said, okay, let's add 3.5 and 4, we would have gotten a very different number. We would have said, okay, so I know that 3 and 4, I know that 3 and 3 make 6. 4 is 1 more than 3, so I'm going to know that that is 1 more than 6, which would be 7. I have a half. Julia's sister is 7.5. 7.5 what? If we don't have the units, we don't have anything that we can compare it to. We can't say that she's 7.5 inches, feet. We don't know. And our comparison would be way off. If we were saying that this is 7.5 inches, then she would definitely not be tall enough to ride the ride. In fact, she would be a medical miracle, and it would be disturbing. But also, she, if it was 7.5 feet, also kind of disturbing, then we would also have difficulty because our initial comparison is with inches. So it's really, really important with measurement, no matter what you are measuring. If you are measuring length, if you are measuring liquid volume, if you are measuring mass, if you are measuring anything at all, please, please, please make sure to always check the units. And that's going to also be important in your answer. Always, always, always include the units in your answer. So you're going to have to include some kind of label in your answer for it to be complete. So if a question is asking you how many feet go around the perimeter of the fence line, you're going to want to write feet, because otherwise, if you leave it blank, or it would be perimeter in what? Inches, feet, yards, miles. We don't know. So labels are extremely important when you are working with measurements. Okay, we're going to go ahead and move on, and we're going to skip the next page because the next page deals more with length, and we've kind of already done a length problem. So I'd like for you to please go ahead and turn to page, oh, my pen is dying, 264. So now we're going to be solving a problem with liquid volume. So the problem in the yellow box says, Marco, Javier, and Jim are going to a party. Marco brings 1.5 liters of lemonade. Javier brings a 2-liter bottle of lemonade, and Jim brings 450 milliliters of lemonade. How many milliliters of lemonade will the boys bring to the party in all? So once again, we have different units of measurement. We have liters and we have milliliters. We have one of the liters is broken up into a whole number and a fractional part. And then we also have a full 2 liters and a full 450 milliliters. So the first step, again, is going to be making sure that we are using the same consistent number of consistent unit of measurement here. So the question is asking how many milliliters. So that means that we are going to be converting all of our liters into milliliters. So below it, it says picture it. You can use a picture to help you think about it. I don't think their picture is super useful because it's just showing you that you have a 1.5 liter bottle, which is slightly smaller than a 2 liter bottle, which is larger than a 450 milliliter bottle. It's really kind of hard to tell because, again, we are having a visual, but we don't know exactly how many milliliters. We're seeing that, yes, there's one that's bigger than the other, that's bigger than the last little one, but we still don't know exactly how to answer the question with that. Below it, it says that you can also model it. So this is a much more useful graphic because it's showing you the conversion for your milliliter. So whereas this one is just showing you a comparison, big, bigger, smallest, down below, this is showing you your conversion for what you are going to use for your units of measurement. So it's telling us that 1 liter, oh, come on, Ben, is equal to 1,000 milliliters. And if you remember our conversation at school, when it's easy to think of milliliters as it sounds like million, but actually mill is the Latin root for 1,000. So if you hear millimeters or milliliters or anything starting with that M-I-L, mill, with the exception of the word million, it's actually going to relate more to 1,000. So one, oh, and look, I didn't have my my label up here. So 1 liter, which is abbreviated by a small l, is equal to 1,000 milliliters. ML is the abbreviation for milliliters. So for every 1 liter, we have 1,000 milliliters. So let's take the first bottle. The first bottle is 1.5 liters. So for every 1 liter, we would have 1,000 milliliters. So 1.5 liters, we have the 1, which would equal 1,000 milliliters, plus 1/2 of a liter, which would be the same as 1/2 of a milliliter. So I'm going to think of what is 1/2 of 1,000. I like to really simplify my problem. So when I see a whole lot of zeros, it confuses my brain and I go, oh my gosh, that's a really big number. I don't know what 1/2 of 1,000 is. So I make the problem simpler. And what I do is I just temporarily ignore these zeros. So I just erase them, but I think, oh, they're still there. I'm going to have to add in 2 more zeros after I do this conversion. But if I narrow down my zeros, I can think, oh, what is 1/2 of 10? I know 1/2 of 10. 10 is like 5 and 5, or 2 5s. So 10 divided by 2 would equal 5. So I'm going to go ahead and write down my 5. But then remember, I said, let's not totally erase those zeros. We're going to keep them in our brain and remember, oh, right, there's those 2 zeros. So I'm going to add on my 2 zeros. And every time I add on a 0, I'm going to add 1 down here too. So that's 1 and 2. So 1/2 of 1,000 would be 500. So the first bottle is going to be 1,000 plus 500 milliliters. If I were to go ahead and add those up, I'm going to try to line up my place values. That makes it so much easier when we're staying organized with our math. I have 1,000 plus 500. I'm going to make sure that my ones place lines up. All of the other places are going to hinge on that ones place being lined up. So I'm even going to write in some lines to make sure that I'm straight. Yep, that looks good. So 0 plus 0, oh, I know that, that's 0. 0 and 0 again, 0. 0 and 5 more. I started with nothing, I added 5 to it, now I have 5. And 1 plus nothing would be 1. So the first bottle, just by itself, I'm going to go ahead and erase this just for clarity, is going to be 1,500 milliliters for just that first bottle. But remember, we want to know how many milliliters total for all 3 bottles. So let's keep going. So now we have our first one converted into milliliters. from liters. Now, I have my conversion here still. I know that 1 liter is equal to 1,000 milliliters. Now, instead of looking at 1.5 liters, rather, I'm going to look at 2 liters. 2 liters, I know 2 is just 2 ones. So I'm going to think I have 1,000 plus another 1,000. Again, I'm going to make that simpler by just thinking, let's take away the zeros. 1 of something plus another of something would make it 2. And in this case, the 2 things that we're adding are thousands. I have 1,000 plus another 1,000 would give me 2 thousands. So I have 2,000 milliliters from the 2-liter bottle. Boom, and we're done. All right, so now I'm going to go ahead and go on over to this board and say I have 1,500 milliliters. I'm adding to that another 2,000 milliliters. And we're almost done. I have 1 more bottle now to add in there. The last bottle is 450 milliliters. Well, guess what? 450 milliliters is already converted into milliliters. I don't need to do anything to that one except add it to my other one. So I have 450 milliliters as well that I'm adding in. So now, once again, I'm making sure that all of my place values are lined up, starting with the 1s. So I have all 3 zeros in the 1s place lined up, and all of my others stacked so that I can see them easily and organize my information that way as well. So again, I'm drawing my guiding lines to make sure that all of my place values are nice and neat in rows, or columns rather. So I have my 3 zeros here. That's going to give me 0. 0 plus 0 plus 5 would be 5. 5 plus 0 plus 4. I know that 5 and 4 makes 9. So adding 0 to it doesn't change that. And 2 and 1 more would make it 3. So they have a total of 3,950 milliliters. And that label, once again, is really important. I'm going to just go ahead and breeze through the questions on the next page, on page 265, because we just answered them. Number 7 says, use the amounts given in the problem to write an equation that shows the total amount of lemonade, T, the boys bring to the party. So this is that algebraic thinking piece again. Remember, with algebra, we are using a letter to stand in for an unknown number. In this case, they're asking us to use a capital T as the total amount of lemonade. So we have T is equal to, if we're going to write it as an equation, you can write it as the numbers equal to T, or T equals the numbers. Remember, that equal sign is really just like a balance. And so it doesn't matter which side of the balance they're on, they just need to equal each other. So we have T is equal to 1 1/2 liters plus 2 liters plus 450 milliliters. Okay, and I think before I said that the abbreviation for liters is a lowercase l. I think it's actually an uppercase L. My bad. Okay, number 8. What units are included in the equation? So we have milliliters and liters that we're comparing. The follow-up part of that question says, which measurements will you convert so that they are all the same unit? Explain. We converted from liters to milliliters, and the reason we did that was because that's what the question asked us to do. So if you go back to the previous page in the yellow box, that question says, how many milliliters of lemonade will the boys bring to the party in all? It's asking for milliliters. So because that's what the problem is asking, we want to make the problem happy, and that's what we're giving it. Number 9 says, show how to find how many milliliters there are in 1 1/2 liters. So once again, we're taking our, we're thinking about our, what we know is we have 1 liter corresponds to 1,000 milliliters. So if we had 1 1/2 liters, we know that we would have 1,000 milliliters for the 1 and half of 1,000 for the half. So we found that out already as 1,500 milliliters. Don't forget your label, teacher Cal. All right. Number 10 says, show how to find how many milliliters there are in 2 liters. Well, for that one, we just said we have 2 liters. So we had 1,000 2 times. So we would have 2,000 milliliters for 2 liters. 11 says, what is the total amount of lemonade the 3 boys brought to the party? So once again, we found that we had 2,000 milliliters plus 1,500 milliliters plus 450 milliliters. They brought a total of 3,950 milliliters to the party. For simplicity's sake, we are going to skip numbers 12 and 13 at the bottom of the page on 265. I highly encourage you guys to answer those on your own time, but just for the sake of our time, I'm going to go ahead and skip those because we still have math to cover and about give or take 15 minutes left of this live stream session. So, so again, I would highly encourage you to come back to page 265 and do problems 12 and 13 for extra practice, particularly if you have already completed some or all of the practice pages, since this is a review lesson. But if you, so yeah, those would definitely be things to do regardless, but especially if you've already completed those practice pages. All right, go ahead and turn the page to page 266. We're on a totally different problem now. We are now dealing with weight and mass. So the problem in the orange box says Kyle has a jar. I'm going to be smart and actually use my eraser instead of my greasy hands all over my whiteboard. All right, getting back to Kyle and his jar of quarters. Kyle has a jar filled with state quarters. He knows when the jar is empty, it has a mass of 900 grams. So the jar just by itself, without anything else in it, weighs 900 grams. But when it is filled with quarters, it has a mass of 2 kilograms. If each quarter has, notice that we have 2 different units of measurement in this problem already. The jar itself is 900 grams. Filled with quarters, it is 2 kilograms. So again, if we were just going by the numbers, we would be going from 900 to 2. That's not going to give us an accurate representation of what, because the jar isn't going to weigh less with more things in it. It's going to weigh more. So that's why those units of measurement are really important. Continuing on, it says, if each quarter has a mass of about 5 grams, about how many quarters are in the jar. So notice that that word about is telling us that we are giving an estimate. So we are estimating, it's saying that each quarter is around 5 grams, give or take. It might be a little bit more, it might be a little bit less, but on average, if we were to take all of the quarters and weigh them out, they would all be around 5 grams. So we are going to be getting, because we have an approximate weight for each of the quarters, if we were going to go by just the weight of the filled jar, then we are getting an approximate answer of how many quarters are in it. If we really wanted to be precise, then we would take the time to count out all of the quarters. But right now we're just getting an approximate idea of how many quarters are in the jar based on the weight. So below the problem, you see that there is something that says picture it. So again, not the most effective tool for solving the problem because it's just giving you an idea. So picture it, you have a 5 gram quarter, you have a 900 gram empty jar, and you have a full jar that weighs 2 kilograms. Not super useful information that we could, it's mostly just a visual representation of what we just read, not something that is necessarily going to help us solve the problem. Below that, though, there is something that where it says model it, is a little bit more useful. And again, using it in terms of algebraic thinking, they have this nice bar model that's showing you that you have the mass of quarters, and they have it written as 5n. When you see a number next to a letter, that means that they're multiplying. So 5n means the number of the number of quarters that we have times 5, because each quarter, remember, weighs approximately 5 grams. So we have the mass of the quarters is 5 times however many number of quarters there are, plus the mass of the empty jar, which is 900 grams. And then all together, all of those things combined, the mass of the quarters and the mass of the empty jar weighs 2 kilograms. So really what we're trying to figure out here, we know that altogether it's 2 kilograms. 2 kilograms take away the 900 grams, and that number times 5 is going to get us a total of 2 kilograms. Now there's a lot of pieces of information in this problem that we need to figure out first. So the first step is going to be to convert, because we're dealing with 5 grams for each quarter, and we're dealing with 900 grams for the empty jar. So what are the units that we're using for those? Grams. So we are going to want to convert our kilograms into grams so that we have a consistent form of measurement. We do not want to go the other way, because then we will not be able to figure out, since it's going up in increment, we need it to be an equal comparison. And since we don't know how, we would again be dealing in fractional parts of kilograms if we were to try to figure out how 5 grams is what part of 2 kilograms. At the bottom of that little model it area, it tells you, it reminds you, it says, remember that 1 kilogram is equal to 1,000 grams. So just like we talked about milliliters and liters, if you're going the other way, so if you have milliliters, then that means that you have 1,000 liters, right? So mil is 1,000. But we also have kiloliters and kilograms. So in this case, we have a gram is our unit of measurement. We could have milligrams, which are so tiny because 1,000 of them makes up 1 gram. But then we also have 1,000 grams is equal to 1 kilogram. You would have the same thing for liters and kiloliters and meters and kilometers, kilometers, some people pronounce it that way. So you would have 1,000 meters per kilometer. You would have 1,000 millimeters per meter. So it would go millimeters would be 1,000 equals meters, 1 meter, and 1,000 meters would equal 1 kilometer. So yeah, so they're reminding you of that. Let's go ahead and work through our problem. So once again, as I said, our first step is going to be to change kilograms into grams. So we just discovered, if you didn't already know it, that 1 kilogram is equal to 1,000 grams. So if we have 1 kilogram is equal to 1,000 grams, we know that we have 2 kilograms. So again, we're going to think of it as our top numbers doubled. So I have 1 kilogram times 2 is going to equal 2 kilograms. 1,000 grams times 2 would be like 1,000 plus another 1,000. I'm going to have 2,000 grams equaling 2 kilograms. So our total weight of our full jar is going to be 2,000 grams. That is a funny looking G. There we go. 2,000 grams is going to be the total weight of the jar and all of the quarters in it. So now we can kind of go ahead and start setting up our equation. Remember, your equation is like a balance. So I have a certain number of quarters that all weigh about 5 grams. So 5N, remember, is going to be what we're using to say the number of quarters times 5, the weight of each quarter, plus 900 grams equals 2,000 grams. So remember that that bar model was saying that we had the 900 plus the 5N equals the 2 grams. This way I've just written it out so that we can go ahead and get an idea of it with our equation. So I have 5N, is the number of quarters, I don't know why I keep saying nickels, times 5 grams for each quarter, plus the 900 grams for the jar equals a total weight of 2,000 grams. So now we're going to kind of work backwards so that we can find out what that N would be. So the first step is going to be, I'm going to say we're going to take away the 900. And remember how that equal sign is like a balance. So if I take away the 900 on this side, if I have 900 take away 900, I don't have it anymore, right? It's gone. And so that simplifies this part of my equation. But I have to do it to the other side as well. So 2,000 take away 900. Now, I would need to regroup for this one, but I'm going to go ahead and use my trick of simplifying by ignoring the zeros for a second. And I'm going to think about what's 20 take away 9. Well, I know that 10 plus 10 is the same as 20. 9 is 1 less than 20. So I would have to add 1 more to make it equal 20, right? So 10 and 10 makes 20. 9 is 1 less than 10. And so in order for it to still equal 20, I would need to add 1 more to the other 10 that I would have to make 20. So 20 take away 9, I know is 11. You can do this a different way. I'm just sharing with you how I think of it. Some of it may make sense to some of you. It may not make sense to some of you. That's the beauty of math, is that you can get to the same answer in multiple different ways. I'm just doing it in the way that I think is the easiest. But again, if it's confusing logic for you, don't do it that way. So now remember, I need to add in my extra zero. So I have 2 other zeros that I'm going to add on. And so I'm going to add 2 zeros to my answer. So 2,000 take away 900 is going to be 1,100 grams. So I now know that the number of quarters that I have times the weight, 5 grams, is going to equal 1,100 grams, because that's the total weight. Take away the weight of the jar. So now we're just left with the weight of the quarters themselves. But we don't know how many. So we know that I have that each quarter weighs about 5 grams, but we don't know how many we have. We just know that all together it equals 1,100 grams. So now my next step in simplifying is that I'm going to go ahead and do, once again, do the same thing to both sides of my scale. So on this side, if I wanted to figure out what 5N was, I would need to, if I'm multiplying, the opposite of multiplication is division. So I would need to divide this side by 5. Just like before, I had adding 900. I took away the 900. I did the opposite to get rid of it. So on this side, I'm going to take my 5 and divide it by 5 here. But I also have to divide this side by 5 as well. Okay? So that's going to get rid of it on this side. And now I'm just going to be left with what the number of quarters is. So I have 1,100 grams divided by 5 grams is going to tell us the number of quarters that I have. So once again, I look at 1,100 and I go, I don't know how to divide that by 5. So I'm going to make it simpler.
I'm going to go ahead and erase one of the zeros, because if I erase both of the zeros, then I'm stuck with 11 divided by 5, and I know that I can't do that. But I do know that 110, I know that 10 can be divided by 5, and I know that 100 can be divided by 5. So once again, I'm going to use that distributive property of multiplication to break up, that says that I can break up my numbers however I want to make the problem easier. So I'm going to think of 110 as 110, and I'm going to think of what times 5 equals 10 and what times 5 equals 100. So 5 times something equals 100, and 5 times something equals 10. And together, my two question marks are going to get me what the total number is that I would get when I divide 110 by 5. So if I'm thinking about it in terms of, oh, you know what? I still don't like that one. That one's too hard. It's got too many zeros. I'm going to go into the simple one first, and then we'll see if that can help me with the other one. So I have 5 times something equals 10. Well, I know from my doubles facts that 5 two times, 5 plus 5 makes 10. So I'm going to say 5 times 2 equals 10. Now I'm going to use what I know from this problem to inform this one, because I'm going to temporarily ignore the 0, because 100 is just like 10 with an extra 0, right? So I'm going to use that 0, and remember that I have to add a 0 at the end, but I have 5 times something equals 10. Oh, we just did that. 5 times 2 equals 10. So I'm going to erase this one. Oh, but remember, I have that other 0 that I have to put back in, so I'm going to put it in here, and I'm going to put it in here. So now 5 times 20 equals 100. So now I'm going to take the two answers that I got, and I now know that 110 divided by 5 is going to be 22, because I have 20 plus the 2 from breaking up my number. Now I need to go ahead and add them back together. So n equals 22, or the number of quarters in this jar is about 22. So if all 22 of those weigh about 5 grams, then we would get the total, add that to the weight of the jar for a total of 2,000 grams or 2 kilograms. If you found that confusing, we're going to go ahead and step it through with the problems in your book. So, so don't fear. So number 14 says, remember that the units need to be the same in order to add or subtract them. So the mass of the empty jar is 900 grams. We can see that from our problem. And the total mass of the filled jar is 2 kilograms or blank grams. So if we already did that conversion, we know that 2 for every 1 kilogram, we have 1,000 grams. So 2 kilograms would be 2,000 grams. So you can go ahead and write in 2,000 on that second line. 2 kilograms is equal to 2,000 grams. Number 15 says, write an equation to show that the mass of the quarters alone plus the mass of the empty jar equals the mass of the filled jar. So they're asking you to write a different equation. So we're going to go ahead and use a different letter, because it says write an equation to show the mass of the quarters alone. So that would just be the weight of the quarter. So without dividing it into that each quarter weighs 5 grams, they're just saying give just a total weight for the quarter. So we're just going to use Q. Q is the weight of the quarters plus the 900 grams that the jar weighs. Together, both of those things equal the 2 kilograms, or if we're going to keep our units consistent, would equal 2,000 grams. Okay. Number 16 says, what is the mass of the quarters alone? So again, we would take the 2,000 and take away the 900 that we're adding to it. So because remember, on this side, we have the mass of the quarters plus the 900 for the jar is going to equal 2,000. Let's take away the weight of the jar. So we're going to take away the weight of the jar here, but we also need to do it on the other side. So 2,000 take away 900 grams. And we already worked through that. Remember, I made the problem simpler by getting rid of zeros temporarily and saying, okay, what is 20 take away 9? We would get 11. Add in those 2 extra zeros, and it becomes 1,100 grams. So the weight of the quarters is equal to 1,100 grams. Oops. Really sloppy, teacher Jazz. Trying to get more coffee. Oh, look at that. I have some right here. And it's cold. Okay. So I have quarters equals 1,100 grams now, the total weight of the quarters, but we want to figure out how many quarters because we know that they each weigh about 5 grams. So on number 17, it says, write an equation to show that the number of quarters times 5 grams equals the total mass of the quarters. So basically, we're just taking this Q and we're saying that that's going to be N times 5. Right? So remember how we had it as 5n earlier? That's the same way as saying n times 5. So then we would want to see how, if we were going to keep our equal sign balance, once again, we're going to divide each side by 5. That's going to get rid of the 5 on this side. Divide by 5 on this side. If I ignore one of my zeros and make this 100 plus 10, I know that 5 times 20 is 100 and 5 times 2 equals 10. I would have an answer of 22 grams. N equals 22 grams. Getting out of control. Okay. 18 says, describe the 3 steps you use to solve the problem. I want you to just be really simple with this. I do want you to answer this one because just like with our performance tasks, how this is clarifying your thinking. This is mapping out what you did first, what you did next, what you did last. So I want you to use those words. First, I converted the 2 kilograms into 2,000 rather grams. So you could even simplify it more than that by just saying, first, I converted the total number of kilograms into grams. I think it's actually easier to say it is 2 kilograms into 2,000 grams, but word it how you would like. But the first step is we converted the total number of kilograms into grams. Second, the next step. So then I subtracted to find the mass. Then I subtracted the mass of the jar to find the mass of the quarters. So we took away the weight of the jar so that we could see how much was just the weight of the quarters. And then the last step is I divided the mass by 5 to find the number of quarters, because remember 5 was the weight for each quarter. And so if we divided it by 5, we would find the total number of quarters that times 5 would equal that amount. Okay, we are just about, not just about, we are at the end of our time. I want to make sure that I can switch over to Google Hangouts to answer your questions. Once again, there are 2 problems on the bottom of this page, number 19 and 20, that I would highly encourage you all to complete on your own, particularly if these practice pages that I'm about to assign you have already completed. So I'm also going to start with a disclaimer. I know that typically in class, I try to keep the assignment to about 2 practice pages. But like I said, this particular lesson covered 3 different things. And so that's kind of a lot. So I actually have 4 practice pages that I'm going to assign to you, one of which is optional but recommended. The other 3 would go along with each of the strands that we focused on: length, liquid volume, mass. Okay, so 1 practice page for each type of unit. The first practice page is for converting units. And as I said, that's optional, but I would highly recommend it because the more practice you get converting measurements, the better. So I'm going to give you the page numbers. Remember that the pages are double-sided. So there's going to be 2 page numbers for one double-sided page. These pages may have already been pulled from your math practice books. They may be loose pages, or they may be included in your math folders because, like I said, I think this is a review lesson, and so you probably already have gotten started on them. If you have, I would encourage you to go back into your instruction book and do some of the practice pages. Even at the end of the lesson, there are the problems there's like a green border around it. So I would even encourage you guys to go back and do that for some extra practice as well. So the practice pages that I would recommend, the optional but recommended page is 269 to 270. The 3 pages that cover the 3 strands would be 271 to 272, 273 to 274, and 275 to 276. So in total, you would be doing pages 269 to 276. But 269 to 270 would be that optional page. So for sure doing 271 to 276. Okay, I'm going to go ahead and end this stream. I'm going to pop on over to Google Hangouts. If you have additional questions, please find me there. If not, I hope you guys have a great day, and I'll talk to you next week at the same time for another math lesson. Okay, bye.